Okay. So you don't actually have to make this one yet. I'll let you know when we get to the parts where making models will help you. Okay. So what we're going to be talking about today is symmetry. That's actually what we're going to be starting with, and then that leads into spectroscopy. Okay. Do you guys remember chirality back in general organic chemistry? That was a symmetry element created by symmetry. Okay. So that was actually light being bent in a specific way due to symmetry. The things we're going to start getting into. Okay, so the first thing I need to do is I need to start establishing the different elements of symmetry. Many of these you're going to recognize, but you're going to go, wow, organic chemistry was so informal with this stuff and so sort of loosey-goosey. And it is true. All of this stuff we're getting into really in this course, we're more formalizing things so you don't have this like loosey-goosey definitions that are circular oftentimes and kind of bullshit. Because that's what the previous courses were, right? We introduced you to the concepts, but the definitions, the how you looked at it was actually really oftentimes circular and some degree of incorrect, right? Yeah. So identity, this is I exist. I have 3 dimensions, okay? And so this is actually you being multiplied by 1, right? This is the molecule being multiplied by 1. It is, I hold up my molecule. Congratulations, my molecule is. Okay? Nothing moves, nothing does anything. Done. Right. Everybody comfortable with identity? Okay, in many ways, identity is actually something that needs to exist for the math to work. Okay, without identity, all the math becomes very difficult and doesn't work. Okay. All right, so let's go ahead and look at a proper rotation. Now, I do not know if you'll actually be able to build this in your kits. This is a benzene ring, right? Your kits... you can kind of. You don't have enough items to fully build it, but you'd actually build it with single bonds between each, and then you'd build it with double bonds above. So if you want to look, this right here is a single bond. Okay? It's the little one. And then you use that between things. And then the double bonds are the longer ones. At least they should be. We'll see if it actually works. Nope, that one doesn't work. That sucks.
What are the purple ones?
The purples are usually used for things like iodine. Yeah. The black is usually carbon. Red is usually oxygen. And those little white balls, those are hydrogens. Okay. Though a lot of people use those for like, the green ones are usually fluorine. That's why they look like a hydrogen, but different color. Okay. These are orbitals, by the way. You can use them for things like lone pairs. Okay. All right, so I guess in these kits, the flexible ones are actually meant for making rings. They don't have double bond bonds for you to use, which is too bad. The kits that I recommended you guys, you can make double bonds with them. So that's really kind of why you want them, as they're very useful for that. And they have more options. Okay, so if you go around, ooh, I have just enough carbons to make my ring. It's a miracle. Okay. So if you go around, you can make your ring probably. You'll probably just have barely enough carbons to do it. Okay, you can make it with the short bonds or the longer bonds. Either way, it'll work. Now, what you'll notice here is if you put this down, you'll have a nice solid surface to get flat, right? and flatten it out because we're going to be working with a flat ring benzene, right? Okay, so what you'll see here is if you have the primary axis, okay, the principal axis. Now the principal axis is this one that goes straight through the middle of the molecule, and it has the greatest rotational symmetry around it. It also has the most mass being rotated usually in terms of where things are rotating. And so what you're going to see here is we have a C6. That 6 is actually the 360 degrees divided by 6. Okay? So every rotation in a C6, see, I'm going to rotate this one, right, would be a 60-degree rotation. Everybody see it okay? Okay. I'm going to go ahead and change one of my colors to blue. Everybody okay with that? You don't have to do it, but I'm going to do it so you can keep track of the change. Okay? So this would be a C6 rotation where we rotate it one increment each time. And can everybody see that it looks the exact same every time we do that, doesn't it? Okay. Okay. So that right there is what's called rotational symmetry, or a proper rotation. It's always denoted by C, and then you put the number of rotations in 360 degrees you could accomplish. So in this case, we have 6 carbons that can match up, so we have C6. Okay, let's look at the C2s real quick. So we actually have some C2 rotations that are possible. We have one where we have the axis going through here. Can everybody see that? And so if we rotate 180 degrees, it looks the exact same, doesn't it? Everybody see that okay? Okay. Now, notice we can do that with every single one of the carbons, can't we? Okay. So we actually have 3 of those that are occurring. 3 axes of rotation there. Okay. Does everybody understand why we don't have 6 of them? Because it's passing through 2 carbons, isn't it? So like if we were to flip this completely, it would be the same rotational axes, wouldn't we? Okay. Okay, the other C2 that happens is going to be the C2 with a double prime, and this is going to be where our axis goes between the bonds. Okay? And so this would be around this axis. Everybody see it okay? Okay. So everybody starting to see the rotational axes? Okay, fantastic. All right, so now whenever we look at the principal axes, these are always going to have collinear axes that can add up to those. Okay? That can have products of that. So for example, when we have a C6, instead of rotating it 60 degrees and it matching, we could rotate it like 120 degrees, right? Or 180 degrees. And we'd still get that matching, wouldn't we? Right? So we can always have the multiples of that. Right? And that's what you're seeing here. So there's a C3 and a C2 that are all on that axis. Those all function, don't they? As a function of that C6 there. Okay. Is everybody okay with the proper rotation? Mm-hmm.
So C3 is just saying it's moving 120 degrees?
Yeah, 3 times 60, or 360 divided by 3. Yeah. So whenever you look at these notations, always remember it's this right here. If you're going to do radians, you can do radians if you like. 2 pi over n, right? Otherwise, that would be 360 divided by n, if you're in degrees. Okay. Okay. And so, for example, C6 would be 360 divided by 6, which is 60-degree rotations each time. C3, 120. Everybody okay with that? C2, 180. Okay. Okay. Fantastic. All right. All right. So whenever we do these, one of the things you have to remember that these are going to be symmetry operations. They can be multiplied together, but they're not multiplied like the traditional multiplication rules. They're multiplied like vector rules, okay? And so order of operation very much matters, right? So for example, if we take two C6 rotations performed in succession, okay, so let's go ahead and do that real quick, okay? Everybody ready? Take your model, rotate it 60 degrees. That's 1, right? Rotate it 60 degrees again, 2. How many degrees did we rotate it? 120. And so that would be a C3 rotation, wouldn't it? Okay. And then you can do the same thing 3 times, and that would be a 180-degree rotation, right? And so notice if you take 2 C6s, you're going to get out a C3, aren't you? Okay. If you take 3 C6s, C2, right? Will be your answer to that product. Okay. Keep in mind that these 6s here, they're divide bys, right? They're on the bottoms. Okay. So you got to keep that in mind when you're doing these things. It's one of the things that really trips people up when they're first starting this. Like C6, this number should be bigger. No. Because you're taking 360 divide by 6, right? Okay. Okay, so let's try an example of this. Identify all the proper rotational axes in the square planar PTCL4 to minus. So I told you the geometry, so you don't really have to do anything extra with that, okay? So this is a square that exists in one plane, right? Okay. Indicate which is the principal axis, then show the following multiplication of symmetry operations that are going to be valid. For example, a C4 times a C4 would give you a C2, right? If we take 4 C4s, what does that give you? Yeah, we would end up just going all the way back to the start, wouldn't we? Yeah, you go the full 360, don't you? So if you did 6 C6s, that would be 360 degrees, right? 2 C2s, 360 degrees again, right? And so whenever you go back to your original state, you always end up with the identity, okay? Because it'd be 360 divided by 360, 1, right? You're multiplying by 1. Okay. And that's why the identity was the first thing we had to do, because if you do any of these enough times, you're going to get back to your identity, right? If you transform it over and over, eventually you can get back to your identity. Yeah. Okay. And so let's go ahead and try this out real quick, okay? So this is what our molecule looks like, right? Can everybody see that square planar? Looks like a square on one plane, has 4 things around it, right? Okay. And this is why I was talking about things like C4s, right? Is because if you have 4 things around it, then you can rotate 4 times, can't you? And you'll match up. Mm-hmm.
This has 2 lone pairs?
The lone pairs don't matter because the lone pairs are not fixed.
Okay.
Yeah. So the lone pairs are above and below. And we don't have to account for them because they're just going to be orbital space where the electrons are just bouncing around, right? Okay. But they do matter in the sense that, like, this is what creates our geometry. Is that making sense? Okay. And so if you have a C4, then automatically you end up having a C2 here too, don't you? Because if we can do a 4 rotation, we can do 2 rotations and match up. Okay? We couldn't have, for example, a C3 though, could we? If we did 100 and that wouldn't give us 180, would it? That wouldn't match us back up. Everybody see that? Okay. Okay, so let's go and look at this right now. So for a square, do you guys need models? If you want to make a model, you can. Otherwise, if this is good enough to do it, then feel free to just use this, okay? if you take a model in your own hands, it usually does help people out. Now, this is one place you guys might have to go, hey, Dr. Clausen, I don't have the ability to do that in my head. Okay? I'm 186 IQ for this. Okay. So I can fully do all these transformations in my head. No objects. Okay? Okay. So this is going to be like a plus symbol, right? And so you rotate the plus symbol, you're going to have two places where it matches, right? Okay. So that's going to be your C2. You designate the differences between these different functions by putting a prime, okay? So this is our first C2 we're identifying, so we put C2 prime. All right. Okay. Everybody comfortable with our C2s? Okay. You will notice there's actually two of these C2s right here because we can have the plus symbol going up and down, right? Okay. That would be the vertical, if you will. And then the other one, which would be the horizontal axis, right? Where we're flipping it this way. Okay, let's go ahead and make it real quick. Do I have one? Let's see. Yep, that one's square. Okay.
You said those are the charges? Is that what you were talking about?
The two minuses here?
Yeah, okay.
The 2 minus is the charge, yeah. But no, I'm talking about the C2 symmetry elements, the C2 prime. You have one that's horizontal, one that's vertical.
Right.
Okay.
And those bonds are rotating.
Hmm?
Is that what you're saying? Those bonds are rotating?
Yeah, you rotate around those bonds. Here, let's go ahead and make our model real quick. Okay. Okay. So go ahead and get a model in front of you. And I'm just going to use, I don't have enough of those. I'm going to use one of these as hydrogens so you can see the rotations, okay? A little easier. Okay, so that's like our model, right? It's a little plus sign. Everybody see that okay? Okay. When we're on the top of it, we can freely rotate that around 4 times, right? And it matches up each time. And that's our C4. Everybody okay with that? Okay. Now, when we go the other direction, I'm going to do it different than the screen because you'll be able to see this easier, right? Okay. So see, you're looking down the bond now, aren't you? That's where our axis is going through. That would be like the vertical axis, okay? And we can rotate it once around. 180-degree rotation, right? And it matches back up. See that? Okay, now we can also do it the other way, can't we? Everybody see that one? Okay, that right there is your second C2 prime. It has the same bond designation, but you'd have one in the horizontal, one in the vertical, right? Okay, and those two are equivalent. Can everybody see that? You could like flip this and it'd be the exact same ones, right? Okay. Now we also have another C2 double prime. This is a different axis and very distinctly different, right? And that's going to be going through between the bonds, like this. So instead of the plus, you have a time symbol, right? An X. Okay? And that's going to rotate like that. Can everybody see how that matches up still? And that's a 180-degree rotation again, isn't it? So we have a C2 that goes this way. We have one that goes this way. Again, we'd have a horizontal and vertical one way. Okay. Everybody okay with that so far? Okay. You see why I highly recommend kits with such verbose recommendation? Uh-huh.
How is that different from the original C2?
Because it's not through a bond.
I mean, so at the like the one next to the C4.
Oh, this one right here is actually 180 degree around that same axis as the C4. So this one is actually through the very center above.
Oh, like the Z-axis.
Yeah. Let me go ahead and put a long bond there. Like this. Like a fan. Is that making sense?
Hmm.
That one does go through the lone pair, by the way.
Okay.
Yeah. So the orbital of the lone pair would be a defining feature of that axis. Okay. And so we can actually see, if we look very closely, we can get different transformations of these. This is actually how we get the C4 versus the C2. So this would be your C4s, and that would be your C2 going through that same axis, right? Just two C4s. And if we go the other way, we get back to identity, don't we? Everybody comfortable with that diagram? These are kind of useful diagrams for writing out three-dimensional transformations in a page, right? Because they give you the cyclic of the transformation. So all this is you're just doing this rotation one time each of these side ones. One rotation, one rotation, one rotation, 60 degrees each, right? And then two of these would be your I'm sorry, not 60 degrees each, excuse me. Divide by 4. 90 degrees each. So 90, 90 gives you 180, right? 90, 90 gives you 360. Back to identity. Okay. Okay. Everybody doing okay there? Fantastic. Yeah, this is the part that's really a slow burn. Most people have their three-dimensional IQ sort of regressed because we don't do a whole lot with it. Yeah, but it'll come back. Okay, you just got to practice it, right? You got to build it like any muscle. You've atrophied it because you haven't really done a whole lot with it, but you'll build it back. Okay? Okay, so the next transformation is going to be a reflection. Now, reflection's kind of an interesting one because this is the one you guys are probably most familiar with, actually. Right, so reflection is this symbol here. Everybody okay with that so far? Everybody see that symbol okay? Okay. All right, so that's going to be when one mirror plane in a molecule. The molecular planes are going to be divided into classes. That's going to be based on the geometric considerations, given subscripts to order then distinguish them. In this case, we're not going to have 2s and 3s that can nicely be defined. We're going to have to cut this up into horizontal and vertical. Now, one of the important things we need to understand when we're cutting things into horizontal and vertical is that molecules exist where they are freely rotating and spinning, right? Okay. So what we need to do is we need to identify our vertical and horizontal from within the molecule, right? Something about the molecule. And how we're going to do that in symmetry is we're going to identify that as our primary axis. Remember the one that had the most spins around it? That's our primary axis. Okay? Okay. So the horizontal one is going to be perpendicular to our primary axis. For our previous molecule we were just on, we had our primary axis going down through it, right? That was that C4. Remember that one? Okay. So if we go through then perpendicular to it, it's this one, isn't it? See that okay? Okay. Okay, if we go down horizontal to it, if we go down the vertical one, that's going to contain our principal axis. It's going to be this. Everybody see that? It'll contain our axis. So, for example, see this right here is our axis, right? It would be planes that chop this in half. Chop, chop, chop. Okay? So those would be our reflections, that are planes that contain our primary axis. Okay, so there can only ever be one horizontal mirror plane in a molecule. This is a very special one. It defines the molecule if you have it. The vertical mirror planes, on the other hand, are going to always contain our principal axis and can actually be quite a few. You can have a huge number of them. In fact, you can go to infinity. Can anybody tell me a molecule that could go to infinity? for number of planes through it. What if I had a straight line? How many planes go through this? That would give you mirror images. Infinite, right? Yeah. So if you get a simple enough structure, you can actually get a tremendous number of these. Okay, so this right here would be the horizontal plane of reflection, okay, or plane of symmetry. This is that plane of symmetry that you may remember from organic chemistry. Okay? Remember the rules for diastemer and enantiomers, mentioned planes of symmetry. Yeah. These are the planes of symmetry. Okay, so this one right here is horizontal. Your primary axis is coming out towards you, right? Right where my dot is. Can everybody see it okay? And that would be your C6, rotating this around, right? Okay. And so the one that's perpendicular, the one that's the plane of the paper itself, that is actually your horizontal, or H, plane of symmetry, right? Or mirror plane of reflection. Okay. Around this plane, if you were to look at this structure, you would get a mirror image, right? That could be freely superimposed. Everybody okay with that? Okay. Notice this one's going to give you something that can freely be superimposed. This is why this was incompatible with chirality. You guys remember that plane of symmetry, you can't have chirality? Need 4 different things around it? Because you have a reflection that can be superimposed. You can't get the reflection that can't be superimposed then, can you? Okay? So this actually kills that chirality. This right here then is the vertical ones. Notice you have several vertical ones that are going through the atoms in this case. And so these are typically defined as vertical mirror planes. And then if you have another one, that would be a vertical mirror plane. And they're the ones that cut through where there's no atoms. Those are normally what are called the dihedral ones. Okay? So these are the dihedral ones right there. Notice they're vertical planes like the other ones. They're just the ones that go through the bonds versus the ones that go through the carbons. Okay? Because you got 2 options, don't you? Right. If you have more options and you can't easily to separate these things, you'd start using primes. Okay? Okay, so the next operation we're going to do is we're going to do an inversion. So this is the inversion operation. It has a symbol of I. You're going to take point X, Y, and Z, and you're going to convert it to the negatives. Okay? So essentially, you're just going to flip everything across. Making more sense? There can only be one inversion center, and it can only occur in the exact center of your molecule, because anywhere else is by definition not going to give you a non-superimposable mirror image. So right here, what we're seeing is an inversion. So see, F and C are directly across from each other, so we'd swap those. This would have a negative X. This one would have a positive X, right? Can everybody see it okay? So we just swap over every coordinate. Okay. This one's actually easier to do by writing it. A lot more difficult to do with the model. Okay.
What about the bonds?
They just freely, we don't really care because they'll get reestablished when we, yeah. You can actually do, in this case, you can do several transformations to do this 3-dimensional. You can do a rotation and a spin to end up getting the same sort of structure. Yeah. And so if this does have an inversion center, the bonds will always freely come along. Because remember, you're moving this one, but you're also moving all the ones around it, right? Can you see how that would reestablish your bonds? Same thing. Okay, so like done, 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 right? So this bond comes, that bond comes. Okay. Did that make sense so far? Okay, did I lose anybody in inversions? Okay, fantastic. Okay, so that's your inversion centers. Your improper rotation, this is the one you probably understand the best actually in terms of like actually have done it before. Okay, so your improper rotation, this is going to be denoted by S, and then you're going to have an N. Okay, this N is the same thing as the C's were. So you're going to divide 2 pi divided by N or 360 divided by N. Whatever you want working, I don't really care. Most people do degrees, but I guess if you want it to be radians and special, you can. Okay? Like, nobody wants to be radians. I don't, whatever. But you don't have to use radians. Okay, so what you're going to do is you're going to have the improper rotation. You'll rotate the molecule, and then you're going to reflect the molecule through the mirror plane so that it's perpendicular to the improper rotational axis. Okay? So essentially rotate and then reflect. Okay. And the improper rotation, we actually have a combination of two motions. Of course, we have the rotation, which are the C's, and then we have the reflection, which is those omega symbols, right? So we have reflection, sigma, excuse me. I don't know why I said omega. Because O, I guess. And then we have the rotation, right? So we're combining these two. And that gives us an improper rotation. So an S6 rotation is actually given in our figure, which I'm going to bring up in just a bit. Okay. The first step, though, is performing the S6 operation. So that means rotating it 60 degrees, right? Because 360 divided by 6. And then only after you have both steps, then your object should be back in a position where you can't distinguish that changed. Okay? That's, again, the same looking object. The S6 operation is a unique and distinct symmetry operation. It has its own properties, and it actually has real-world results that change the spectra of these things. Okay? So it is, yes, it's a combination, but it actually is a real thing. Okay? Although it performs your same function as a combination of the reflection horizontal and the C3, it doesn't actually have to be a proper C3. Like if you do the C3, you don't actually have to have a C3. Okay? Okay. So one of the things you have to keep in mind, if you do these improper rotations of S1, this is actually a reflection. So an S1 where you don't rotate it and you just reflect is a reflection, right? And if you do an S2, this is actually an inversion. So technically those would be a subset of these improper rotations, right? Mathematically. Mm-hmm.
So it's like when we just, so like by saying one, we're just leaving it alone and then just reflecting.
Yeah.
Oh.
Yeah. So you're rotating 360 degrees and then reflecting. Yeah. So you didn't accomplish anything with the rotation, and then you're just reflect. Yeah. This one you do 180 degrees, right? Which is similar to an inversion, right? You go the opposite side. And then you reflect to take care of the other axes, right? And so you're doing the switching of x to negative x, y to negative y, etc. This is how you can actually do on a three-dimensional model the inversion, by the way. Yeah. So if you're trying to do the inversion in a three-dimensional model, that's how you do that. 180 degrees, reflect. Okay, this actually gives a really good example that really helps you break that C3, C6 has to be the same sort of thing. Okay? Okay, so right here we have an S6 that's happening. So we rotate it by the 60 degrees. Everybody say it okay? And then we go ahead and reflect, right? And that actually causes it to match up, doesn't it? But if we were to just rotate this the 60 degrees, this wouldn't match up, would it? We don't have a C3. We don't have a C6 even. Okay, we just don't have those. All right. So notice that we don't have that C6, do we? If you rotate this 60 degrees, it's going to give you a triangle in the other way. See that? Your corners would be at sides, wouldn't they? Yeah. So that hopefully helped you break that up in your head, okay? Okay. Anybody recognize this one? Newton projection? Organic chemistry? Oh, shoot. Yeah, we got our tetrahedral structures trained together. We have a Newman projection, right? And then we have the different geometries. Oh, wonderful. Okay, so this is the staggered conformation, the most stable conformation. This is a S6 right here, rotational axis. That's actually what you're looking down when you're looking at a Newman projection. You're using the S6 axes to do this, okay? And so what you would see here is if we rotate this 60 degrees, it still doesn't match up, right? Because they're in different carbons, right? But if we then rotate it, that would then give us our original structure, wouldn't it? Okay? So if we do the reflection, we would get our original structure. Okay. Cool, huh? That was always what that was. Yeah. I know, it's like the chemistries actually blend together. Did anybody need to make that before we move on, or are you okay? Okay. Fantastic. This is actually a tetrahedral structure right here. And we can actually see that S4s are actually what tetrahedral structures are. So the tetrahedral structure with everything symmetric around it is an S4 symmetry. Okay. And so you could then move it by 90 degrees, right? And then do a reflection, and that will always give you the same structure back out. Okay. Anybody have any questions about that, or are we okay? Okay. Those are going to be the primary operators we're going to have to use to build up on. Okay? And so, okay. Did everybody see that I posted that spectroscopy book with the tables? Okay, if you check the chapter on Canvas, I've posted a copy of a 1950s spectroscopy book. And what it has is we're going to get into these operations and point groups and start adding them together. Okay, but mathematically, these things actually multiply and give products, right? So I'm going to give you the one, and this is the inorganic chemist's way to do it. And what you're going to see is they kind of take the full route every time. Okay, so they go through almost the entire full path every time. And then if they're going to do any simplifications, they simplify it down to point groups. They don't go any further in simplifications. Spectroscopists need to do this quick, and they need to be right all the time. Okay? And so they have solved it down, spectroscopists, like 70, 80 years ago, solved this down to simple formulae that you can just plug in the number of atoms that are on specific elements, and it'll always give you the right answer every time. Okay? And so if you look in that book, there's tables where it actually solves down all of this in easy to use methodologies that are just like 5 minutes max. Usually more like a half a minute. Okay? Something that should take you like 3 hours to do on this will take you maybe a minute. Okay? Okay. So keep in mind, though, that please don't just use that. Actually get some practice with these, okay? Because you do need to build up your understanding and ability to model in your head. And that's what this does really nicely. Okay, so these are your symmetry operators again. These are the symmetry elements. That's what happens in each of these. This is the summary table. If you need, you might want to print some of these figures out if you don't want to have to go back and forth in your books whenever you're doing these things. Okay? And most of you are probably going to need these at the beginning. As you get more practice, it won't be as much of an issue. And I'll post homework today, actually, if somebody would be willing to email me and remind me, I'd actually really appreciate that. Because Tuesdays are crazy. Mondays and Tuesdays. Okay. So let's identify the symmetry elements that are present in each of the following ions or molecules. We have the PTCl4. Then we have NH3. NH3 is going to be used in a lot of these next examples. And then we have the CO and then EN 3 times around it, 3 plus. The EN is going to be ethylene diamines, 3 times around it. Okay, so the big thing we need to understand is really what is the type of Vesper structure, right? The molecular geometry, okay? Has anybody sort of picked up that if you had the same molecular geometry, then everything else is the same, isn't it? Like, would it matter if I had OF2 versus OH2? Would that change my symmetry? No. As long as you have the same repeats and the same molecular geometry, you're good, right? Yeah.
Depends on the bulkiness of the atom, but
Not really, because it won't change your symmetries, right?
the angles in the symmetry, but
Yeah, the angles will change, but doesn't really matter, does it? Because you are symmetric.
it'll just be wider or,
Yeah, so you'll still end up with the same symmetry elements. Yeah. And we'll get into that in just a bit. But, yeah. So, if we look at this, the PTCl4, this is going to be square planar, right? And so the elements it will have is, you always have identity, don't you? Everybody okay with that? E identity, it exists. Okay. And then the next things you always have is, you always have, for this one, we're 4 items around, and so we have to be, by it being square planar, right? That one's going to have your C4. Can everybody see that? You can rotate 4 times around that middle axis, right? Okay. That's your C4. Now, if you have a C4, that's going to have a C2 as well. Because if you can rotate 90 degrees 2 times, and that works, then rotating 180 degrees is also going to have to work, right? Okay. Is everybody good to that part? Okay. Okay, now we kind of already did this one, so I'm going to go fairly quick on it. We have 2 of the C2 primes, 1 that is at the top. So we have our C2 primes. These are going to be going through the bonds, right? And then this way. Yeah, and we have 2 of those, don't we? Okay, so we can rotate that. You can rotate that, right?
So I'm sorry, I'm just a little confused. The normal C2, where is that? The normal C4, where is that?
Okay, that's the one going through this way, like a fan. You can rotate that 4 times.
Okay.
See, okay? Yeah, that one.
And then the other ones would be like that and this.
So the other ones are going to be where we take this, and they're going to be perpendicular. And so we can rotate it around this one right here, right? That's C2. We can also take this one and do it. That's the second one of those C2 primes.
Okay.
Okay? And then we have a C2 double prime. This one's got a little hard for me to do because there's nothing to grab, right? But this is the axis that goes like this. Okay? So this is like rotating the X sign. Okay. Not as easy to do physically, but I think you all got it, right? Okay. And so the next one is going to be our reflections, right? And so we have our primary axis, which comes down through, right? In between all 4. Okay. So we have the one that's perpendicular to that. That'll be horizontal. Then we have the verticals. Okay. Notice we're going to have several verticals, right? That can be subdivided here. So we have verticals that go through the atoms, right? The chlorines here, I believe it is. Yeah, chlorines. And then we have verticals that don't actually hit any of the chlorines, do they? But still give us a mirror image. Can everybody see that okay? Okay. The kits help, don't they? Okay. Now, this right here is going to be our, okay, so we have an inversion. Can everybody see the inversion would be? Okay, so all you do is this one's a flat plane, right? So all I have to worry about is moving in the x and y. I don't have to do anything in z. Everything z is 0. Okay, so plus, which side is that for you? It's right side for you? Okay, and that's, are you okay if I say plus x? Minus x. Everybody see that? Y 0, z 0. So you don't have to move either of those, do you? Okay. This one right here would be x and z is 0. Plus y, minus y. And so when you can just flip those, right? Okay. And notice if you just spin it, you end up doing that more for one of them, right? Okay. So if you want to do the inversion with this model kit, what you want to do is do 1 rotation, a 2 rotation, right? And then inversion. See that? Okay. And that's actually what that is. That would be an S2. Okay? So an S2 would be this one right here. So we do 1 rotation, right? And when we do a flip, which gives a reflection. Mm-hmm.
I'm kind of confused on I'm confused on the inversion. So
Okay.
can you give an example of something that's not an inversion?
Yeah, so non-inversion would be this way. I can't do it on this one, but let's get something that does not have an inversion. Okay.
I'm just confused on what would, I guess, qualify.
So it would be where, for example, if this right here actually did have a hydrogen instead of a chlorine.
Okay.
Okay, so it would have rotation like this, right? But if we rotated it, then inverted it, well, that's not a chlorine, is it?
Yeah.
Yeah. And so that's no longer the same thing.
Okay. And so are you going off what you first like?
Yeah.
Going off the first image and the last image?
Yes.
Oh, okay.
Yeah.
So, if it doesn't
So they have to match up so you can't tell the difference anymore.
Oh, okay.
Yeah. Yeah. And all these have to match up so you couldn't tell the difference.
Okay.
Like if you were to look at what it was
Mm-hmm.
and then close your eyes
Mm-hmm.
and not rotate it, you shouldn't be able to tell the difference.
Okay.
And the previous models, I don't have another green one, but these would have all been the chlorides, right?
Yeah.
Yeah. So when you do that for the previous models, it's still the same thing, isn't it?
Okay.
You won't be able to tell the difference.
And if it was that hydrogen?
Yeah, if it had a different atom on that 4th position,
Okay.
yeah, that would break that symmetry. It would break a few of the other symmetries as well, but we'd still have a few of these. Yeah. Mm-hmm.
What is the 2C2 and like what is the 2 in front of that?
It means there's 2 of them.
Oh, okay, so
So, for example, there's one that goes like this, right?
and
And this one.
okay, and then the prime. What does the prime mean again?
So the prime means this one's this one right here, where we're doing it along the molecule, right? That's the axis, is along the atoms.
right.
The other ones where we're doing it,
Oh.
it doesn't hit any of the chlorines.
Okay.
Okay.
So prime 1 is with the atoms.
In this case, it doesn't really matter,
Yeah.
but typically, yeah, you start with the atoms and then you work your way
Okay.
less atoms.
All right.
Yeah. I kind of wish they had done H's and D's here, but there's other things that they needed it for, and I get why. It would have been confusing if you made any mistake in putting it on top or bottom. But anyways, yeah, the primes are just, you're recognizing that you have 2 different sets of axes here. Okay. Okay, so we have our inversion. Everybody's comfortable up to that one? Okay. And then we have our S4 here. And the S's are, again, going to be where we do this improper rotational. So what we're going to do is we're going to do a quarter, right, which is a 90 degree. Everybody okay with that so far? Rotate. Okay.
It's I can do it over time.
So we're going to do a quarter, 90-degree rotation. Okay. And then we're going to do a flip.
Was it
Or reflection.
Horizontal flip? Okay.
Okay. And keep in mind that, again, these are a rotation followed by reflection, right? Okay. And for this one, you can do that actually in 90-degree 4 times around, right? Okay. That making sense? Okay. Okay. Note again the S's here. S1 ends up being these, right? S2 is an inversion. S4, 3, those are actual things. Okay? They're actually different stuff. All right? They're your improper rotations, proper, if you will.
When we're doing these and we're thinking about them,
Mhm.
we're like, I'm picturing an atom like that, and
Mhm.
then am I just picking one element, and then that's what we're rotating and looking through for symmetry, or?
So you're looking at, for rotations, you're looking for an axis to rotate through. And what you should always have for all of these symmetries is that you do the operation, and then if you were to have somebody else do it for you, you wouldn't be able to tell the difference. Okay?
Right, and you're just using that hydrogen just to show.
I don't have a... Somebody want to throw me a green one? Oh. Almost. Okay. So, that's the molecule, right? And so we do the rotation. You can't tell the difference, can you? Yeah. Yeah. I just didn't have another green one. Because my model kit busted open in the move and spilled everywhere. So I'm using the ones in there. Yeah. And so again, if like you do the reflection, right? Okay. And so it's sort of a good way if you know the rotations and reflections and you know how to do them with your hands, okay? If you look at it, close your eyes. I can't tell the difference. Okay? Look at it, close your eyes. Can't tell the difference, can I? And that means you have that symmetry element. If you can do the transformation, and there's no way to tell the difference. Okay. Mm-hmm.
So do the reflections always line up with like the C2 prime and the C2 double prime? Because like we have the one horizontal one which like go with the C2, and we have the two vertical ones to go with the C prime, and then the two C double prime that should go with the cathedral ones.
Mm-hmm.
So like would those always or like match up?
If you have them, okay. So I'm not exactly. We don't quite have the terminology to go through, all the way through this, but essentially, these right here, if they exist, are going to match up with these things,
Okay.
with one of these axes. Yes, but it doesn't necessarily have to be the C4. Okay. Because you could have something that does not reflect even though it has rotations, right? We'll get into character tables later, and you'll be able to see what all the possible combinations are.
Okay.
But yes, if you take these symmetry elements, they have to actually solve within each other. And so you have to actually get all the other ones by taking the ones that you are not including and using them to get that as a product. So, and that is what's called completeness. Okay? But we'll get into symmetry tables in a bit. Okay? We need symmetry elements first. Yeah. Yeah. So, yes, you can get all the other ones from those and solve from. That's actually why those equations exist, is because you can solve them down.
Okay.
Yeah. But it's a bit more complicated. And am I out of time? Yes, I am. Okay. We'll start up here next time. And let me know if you have any questions about the solving of this. And if you haven't bought model kit, if you haven't gotten one, please do. And please bring it to class. It will greatly aid you. Did you need your greenback, or can I steal that? Okay. If you'd be so good as to go ahead and put them back in and put them back in that room for me, that'd be greatly appreciated. And I will see you all next time. And we'll have to try to fly through the material next time.